Thanks for coming out. So before I dive into this, we're going to cover a bit of a summary of modules and modular, the variations of modules that Clang now supports. There are some great talks that cover this, some of which haven't been here at the LLVM dev meeting. Manuel Kalmek, Daniel Jasper, Richard Smith have presented in quite great detail at CPPCon. All of the talks are recorded up on YouTube. And some flavors of this have also been presented here at the dev meeting a couple of years ago by Duncan Smith and Adrian Prantle. So I can point to those later, send out email with links and the like. Does that go on? Excellent. So let's cover a few details about the different flavors of modules that exist in Clang and in various levels of support, just to get some context for what we're doing here. Taking a simple motivating example, you have a header, you have some source files that use it. Classic model is the compiler preprocesses, includes the header in each file, parses all of that code, which in this case is quite simple code, twice or many times, depending on how many times the header is used. That work would be nice not to duplicate and do over and over and over again. So the first version of modules that were implemented by some Apple folks, particularly to improve like system headers like coco.h. And they were done in a way that allowed you to use them without ever touching your build system. This was significant for rollout. Obviously, it's much easier to convince people to use it by just adding a flag or even not telling them. And all you have to do is write a module description for your headers. The compiler will then find that and do a bunch of work to optimize its own processes. And that looks something like this. Build system knows about two source files. It asks the compiler to build the source files. Compiler then notices that the module maps exist, goes off and actually runs the compiler again itself to build the intermediate representation, the PCM file. After that is built, goes back to the original compilation processes and finishes doing the compilation, produces object files like you've seen before. You link them, you get a binary, you move on with your life. This has some limitations. Obviously, it has the advantage that it's very easy to roll out in terms of build systems and everything else. Great. But it does mean that the build system is not aware of what's going on, so it can't fully schedule and parallelize. I'm going to take one diversion here. It would be great if anyone has questions, if they ask them during the talk. There are two mics up here. Feel free to come up to the mics. I'll try to spot you, and we can just discuss things as we go, rather than getting to the end and having people who are confused. So questions during the presentation are great. Anyway, so you write your module maps, the build system does its best, it runs two compilations, but then both of those compilations might pause waiting for a single task to finish. Now obviously if those two compilations depended on two different modules that could be being built in parallel, they aren't. The other thing is that this only works on the local machine. I'm not sure whether it works on machines other than Mac OS, someone can confirm, in terms of it uses a local file system cache to keep track of everything. So it doesn't distribute in any way. Google kind of likes to distribute things, so this didn't really work for us, which is why Mr. Smith finished out the module implementation and built out a different way of doing it, which we've generally called explicit modules. This is where the build system knows what you're doing, and it can orchestrate all of those steps. So it knows how to build the PCM file, it knows how to pass it to the compiler. The compiler doesn't do any kind of extra compilations under the covers. So it looks more like this. Build system sees that you need this. Excuse the file extension. I realize MM is a file extension for Objective-C++, but module map is too long for a slide. So the build system builds your PCM. It then passes it off to two compilations to build your two object files, and you move on with your life. There's another form of modules, which is the modules TS. This is being standardized in the C++ committee, various flavors, still some outstanding kind of things to deal with. But from a practical perspective for this presentation, it has a lot of similarities with the explicit modules. You have to modify your code, you have to modify your build system, and it does actually require modular code generation, which we're going to talk about shortly. Whereas the explicit modules, modular code gen is sort of something you can bolt onto it afterwards. So let's talk about modular code generation. Let's have a look at what it looks like. So to get the motivation for this, let's look about what happens when you don't have modular code generation. Here you have a classic kind of situation. You had your inline function from the example earlier, and you compile two files that use it. Yeah, you got to use your PCM, but F1 ended up in both of your C++, in both of your object files, and then had to be deduplicated by the linker. The linker gets to pick one, but it had to get all of those bytes in the first place. This might not be an issue for local links, but for large distributed links at Google, one of the limitations is all of the bytes shipped to a single machine. So having all of that duplication can be unfortunate in terms of the number of bytes that need to move around, even if they can be skipped. And obviously, even cache lines and disk caches and everything else might be hurt by the fact that now your object files are larger and there's all of these bytes that you need to ignore. As you can see on the left there, another little piece of this is debug information. And this is something Adrian and Duncan presented about a few years ago and that was implemented for implicit modules. When you can modify your debugger, you can implement this for implicit modules in the sense your debugger can now know how to navigate those file system caches and get to the modules and extra debug information. If you don't want to modify your debugger, but you can modify your build system, you have an alternative which also works with this modular code generation. So what you do is your build system knows about PCM files, so you ask it to build an object. And you put F1 and your debug information in this object file. And now you don't need to duplicate it everywhere, and your linker gets exactly one copy. And it links things, and away you go. So this saves a bunch of file size, and all of this seems good. Saves you a bunch of emitting those bytes into the object files in the first place, optimizing those bytes, all of this, which is great. But when I went into this, I knew there was a possibility that it would actually work out for the worse. What happens if your header file contains a bunch of unused functions? You say, why would I write a bunch of unused functions in a header? Anyone heard of protocol buffers? Any other kind of auto-generated code where you might generate a huge slab of code with a bunch of things you might like to use, but you might not always use. That's what this looks like, except, hundreds and thousands of lines longer. So it's possible that the balance in terms of the deduplication you gain versus the extra things you omit but you don't use could skew badly. You could implement this and actually end up sending more bytes to your linker than otherwise. And we didn't really have a good sense. I had some numbers, but it was hard to get a really good sense of what are all the functions that we never actually generated code for that we will start generating code for when we turn this kind of thing on. And I implemented some of this, and I'd evaluated some of it, but I really wanted to get a good sense on a real code base. And so I went and implemented it in Clang using Google's internal build system, but plumbing it out to all of the code base to see what that balance looks like. There are some constraints when you go to do this kind of work. So when you go to modularize your code to begin with, forget about modular code generation, you need to accept that your headers must be what we all consider to be good headers. Like they are standalone, and basically if you imagine, can I include this header in a file without anything else around it, and it does what I want? Okay, great. So you fix all of the situations when that's not true. And you rename your files that you actually want to include in weird ways, which LLVM does a lot, to .def, ideally. So you give them a different extension. You say, these aren't real headers. These are arbitrary bits of text I want to include in files. The next thing, when you go from modules to modular code generation, is you find that you're constrained even further. This caught me by surprise, but maybe it shouldn't have. LLVM does this. It violates layering between its libraries, and it does so by putting headers in a different library from their implementation. And this is subtle and kind of works, and puts more and more code into those headers, because once you put it in a header, it gets duplicated everywhere. And so there's no dependence problem, because you just put it in multiple places. So when you go and don't put it in multiple places, because you've got modular code generation helping you, you actually flush out those kind of layering violations. And just to take a step back, I'm going to revise a famous line inside Google, how Unix linkers work. So let's just take a diversion here. Let's imagine we have a couple of libraries with the following structure. You've got A1 and A2, A1 calls B, B calls A2. And you link them on your Unix linker as you might imagine you would. BFD, gold, will have the same problem. So you start off and you tell the linker, I am calling A1. Let's say A1 is main for the purpose of argument. So it starts off looking for A1. Goes to lib A, finds A1, but A1 needs B. So now its list of things to look for is B. It goes off to lib B, finds B, and now it finds that it needs A2. Unix linkers don't go back again. They just keep going forward. And so what ends up happening is you get a link error. And you stare at your libraries and go, but I totally have A2. What are you talking about? This is the way Unix linkers work. This helps us actually preserve a bunch of layering inside LLVM. But when you turn on modular code generation, this becomes even more important. Because if you have put a modular object file built from a PCM in a different library from the C++ file that implemented that thing, inevitably you will have a circular dependence. You can basically imagine any header file has some inline functions and some non-inline functions. Some of those inline functions call the non-inline functions, and the non-inline functions invariably call the inline functions. A header and its implementation are almost ubiquitously circularly dependent. They need to be in the same library. So this will constrain your C++ further and cause us to have to fix a bunch of our layering violations in LLVM and in other code bases that want to use this kind of functionality. This is probably a good thing, but it is work. How much work? Some of this work. I haven't committed all of these patches yet, and I didn't have to do as much work as it would appear. The implicit module system has been working in the open source for a while. There is a build bot that builds all of Clang and LLVM with implicit modules. So the basic modular kind of cleanup has been done, but the modular codegen constraints start to come out, and you have to fix some of those. So these are some of the things I fixed. Some of it is just porting the internal build system to understand things that are already in the external build system, the module maps that are committed upstream. Google's build system doesn't use user-written module maps. We describe in the build system generates module maps. So we can't use the open source module maps in our build system, so I had to teach it the same things. There are a bunch of headers that are non-modular, that pretend to be modular. The command flags are basically header files full of static CL options that you just dump into an LLVM tool to be like, oh, now I have all the flag support for whatever. What else did I hit? Some layering things, some bunch of missing includes, a bunch of things dependent on includes for definitions of types for pointer unions and things like this. So many things that are static in headers. It's easy, you just make them inline, it's fine. ABI breaking.h, who here is responsible for that one? It's awesome and crazy, and I don't know how to do it in the modular world. I'll just have to give it some more thought for the moment. I've just disabled it to get these numbers. Fun things in Hexagon. They've just got some little bits of headers that may not need to be headers, and at some point I'll have to talk to Manuel about the AST matches, because that's a header full of global variables. That was weird. Results. So numbers. You can see the percentages on the bottom. This is how much smaller the sections of object files in an O0 split dwarf build of the Clang binary got. This is not the debug info, this is only the object files, but built with debug info. So you can see some debug info sections in there, but it's not all of the debug info. So some things, so those percentages aren't how much smaller each section got, they're how much smaller the overall objects got because of the shrink in each section. So this is what it actually looks like all up. So this is I think, about a 16% reduction in object size. You can look across this, it's a bunch of text, it's a bunch of other things. Obviously, you shipped a bunch fewer inline functions. So hey, it helped. We didn't actually have that F1, F2, F3 kind of situation that I was worried about. That's cool. You can see a few other sections in there, but basically everything got a little bit smaller, which is nice. So about that debug information. And Adrian already knows the answer to this. He did it with the implicit modules. It does this. It's great. It gets about 70-something% smaller. I don't have a histogram to show exactly how many duplicate things no longer get emitted duplicately, but suffice to say, a lot less. But I've been lying. Has anyone spot the lie? I didn't talk about optimizations. So that a F1, F2, F3 situation, that comes up even for functions you did call if they then got optimized away. So in your optimized build, maybe it doesn't look so good. So this is the overall debug info if you turn on each feature. And in fact, you'll notice that the features are actually complementary. So while it was a 70-something% and it's 16%, Overall, you get an 80% reduction in split debug info and a 20% reduction in object size for an O0 build. But this is an O3 build. This is unfortunate. Your debug info gets smaller. Great, because there's no way to optimize out debug info. That's cool. Your objects just got larger because so many inline functions got optimized away, and then you just unnecessarily shipped a definition of those inline functions to your linker, which said, I don't need these. Why are you giving me this stuff? But if you notice, it actually almost breaks even. Because so much less debug information is emitted, a small amount of that debug info does actually go into the objects. There's what's called pub names and pub types. And this is for an index so that your debugger can be fast to find all of the things. So if you see that sort of bright blue section, it's about the 5th section over, 6th. It gets really small once you turn on the debug info reduction. That basically offsets, in this particular case, the growth. So it grows by about 7%. The reduction in pub names and pub types is about it grows 6%, reduced by 7%. It's still a reduction by 0.75% on object size. I don't know whether this generalizes, unfortunately, but it's kind of nice that it breaks even, at least. So that's basically the functionality that we have today. And this functionality is useful, obviously, for anyone who has an explicit modules build, which is Google at the moment, but I hope that we'll get CMake and other functionality to support it. And it's also necessary for modules TS as those features are developed. Further work. More pieces in modules TS. Variables have been implemented by Richard, so you can, if you have variables in your modular header, they can be emitted once. Mostly this falls out for backwards compatible explicit modules, in the sense that if you have a variable, like a static variable in an inline function, and you change the linkage of the inline function so that it goes in one place, the variable goes in one place as well, and it all works out. Pretty much the only way to improve that growth in object size is implementing inlining heuristics in the front end. The simplest of those is the always inline attribute. If a function is attributed always inline, there's no real reason to try to home it into the modular object file. Let it be inlined everywhere. Don't provide an extra definition of it because you don't expect to ever need a definition of it. Whether or not there are other reasonable heuristics to implement that might help us not produce redundant definitions into the object files that are never used by the linker, I'm not sure. Does that mean the feature is useless? No, certainly at O0 it's useful. Even at optimized levels, maybe it's still useful in the sense that it gives you a strong definition of where these functions go. People might write fewer inline functions because we have things like thin LTO and LTO. So maybe it's still the right model, even if it grows object size slightly. I'm undecided about that. Another neat trick to do with debug information, and I didn't show it in these slides, is there's a thing called type units, which are a way to allow the linker to deduplicate types much like it deduplicates functions. Type units have some overhead in terms of making the type in the debug information separate so it can be moved around and sliced and diced. And since we now quite often know that a type is only going to be put in one place, we could more intelligently choose not to use a type unit for a type that will never be deduplicated. So that might be nice to implement. That would also potentially improve even non-modular code generation scenarios where a type has a key function and is only emitted in one place. We could, again, avoid that overhead. So that's roughly the size of it. I'd like to thank all the people who helped me work on this. Daniel Jasper implemented some of the internal Google build system support for this. Richard Smith obviously provided with a lot of code review and with a great foundation to work on this. I implemented the functionality in Q1. We did 2 different implementations until we found the right fit, and both of them were incredibly easy to do because of the way the code was laid out. And thanks for coming. Questions at the mics? Hi, Gore.
Is a function level linking might help with that, where you request not entire object file, but just the functions you need, and then they'll transmit it to you, just those functions.
So Langhames and I have talked about this, and some of it is tricky because, again, for a distributed build system like I'm dealing with, you don't know which functions you need, because you need to look at the whole world to know which functions you're ultimately going to need to generate. So you could potentially do a 2-pass step where you like export lists of functions. Maybe I'm misunderstanding the question.
I think I meant more like thinLTO kind, where you import from other nodes of your build system a specific functions this node needs.
Right. So if you had that extra step, so thinLTO, for those who didn't go to one of the thinLTO talks, is basically like you compile everything to IR, then you cross-reference and check which bits you need, and then you do another step where each of those front-end compiles does another sort of a back-end step and imports the right bits. So yes, you could do something like that, and potentially, if you wanted to do something like that, you could produce the AST and then like really lazily do thinLTO, where thinLTO says, I need this function, and you go all the way back into the front end, not just like import this IR. The trick with that was you would still need to do the full call graph discovery. So you'd need to look at the AST for a function and go, oh, it calls these 3 other functions, which I've never even like IR generated or done anything, so that the linker has still full view of the call graph to be able to link. So possible, but it's a bit of a ways off and has some issues.
2 questions, and I already forgot the first, so I'm going to ask the second first and try to remember it.
Sure.
What are your thoughts on templates, which PCM really helps template parsing, but I've thought about this for 30 seconds, is that you can't get the instantiations.
So this is totally agnostic to templates, which is to say that it works with templates. So if you have an instantiation of a template in a PCM, it is considered the home. And so some of the things you home into a PCM aren't unique. So for example, if you instantiate std vector in 2 different modules, those modular object files will have whichever instantiations of the vector int functions you want. But everything that uses that PCM will know that that is the place where vector int is and won't produce another one. So like the sort of like transitive closure of things that depend on some random header that happens to instantiate vector int benefit from that kind of thing. I haven't looked, again, I don't have the full histograms to see like how much deduplication do we reduce.
Second question, which I have remembered.
Awesome.
So Google has infinite build speed, but have you measured improvements in build times from this as well, or de-improvements?
I have not attempted to measure. Mostly I've been focused on object size, because we happen to have some very large programs that are taxing reasonable limits for our build system. So looking at ways of reducing the number of bytes we produce and ship was sort of my motivation going into this.
Thank you.
Yeah.
Well, thank you. That was my question too.
Oh, yeah.
You mentioned CMake support for explicit modules. Do you have an idea for how to implement that?
I know nothing about CMake. I have desires that I would like to use this functionality that I've built for my own builds, as you can see why. I mostly build O0 with split dwarf, and it would be awesome. I don't know enough about CMake to know how hard that will be.
Okay.
Sorry. Anyone else? Once, twice. Thanks for coming.